Hey everybody, welcome to 8th grade algebra. This is our third review for the end of the year. Today we'll be discussing how to solve systems of equations algebraically. Last time, we talked about several things. We talked about what it meant for something to be a solution to one equation in one variable. Then we talked about what it meant to find all of the solutions when there are two variables involved. And in that case, we just drew a graph. Mostly lines. We then talked about what it meant when you had more than one equation and you had to find the variables that satisfied both. We then found some solutions to systems of equations by graphing them and finding the points of intersection. This time, we're going to be talking about what it means. Again, you can't get enough of that. Then we'll be solving by guess and check. We'll be solving by substitution, by elimination, and we'll be interpreting the solution in context. We're going to mix some of these together today because even though you might choose one solution pathway for a given problem, the reality is you could use any or all of these at any time. So to get us started in talking about what it means for something to be the solution to a system of equations, I'm actually going to have you try a problem on your own in Desmos. I'm going to ask you to solve this problem, it's multiple choice, and explain how you know that that's the solution. Take a few minutes, go into Desmos, and your teacher will bring you back here. All right, there's a lot of ways to solve this. Hopefully you found that the answer was C, x equals 1 and y equals 4. But what does it mean for 1 comma 4 to be the solution here? Well, what it means is that it makes the first equation true, and it makes the second equation true. Well, let's check to see if it makes the first equation true. We're going to substitute 1 for x and 4 for y. And what we get is the expression you see here. Let's simplify what's inside of the absolute value. Let's simplify a little further. Let's simplify further. And we get 4 equals 4. That's a true statement. Now let's check to see if it satisfies the second equation, because if it only satisfies 1, it's not a solution to the system. Substitute 1 and 4 again for x and y, simplify, and there you have it. So what it means for something to be a solution to a system of equations is that the values make both equations true. That actually brings us to our first technique, which is we can use guess and check. All we did is we just checked answer choice C and found that it worked. You can use this with any type of equation, even if you have quadratic equations or linear equations all mixed together. It works well with easy to calculate numbers because you don't have to do a whole lot of arithmetic when checking. It's really great for multiple choice, like the example that we had here. If we wanted, some of you might have actually tried A, tried B, tried C and D, and found that C worked. One of the drawbacks of guess and check is that sometimes it's difficult to determine if there are multiple solutions or no solution. So now let's talk about the second technique we can use to solve a system of equations algebraically, which is by using something called substitution. Substitution works like this. If you're trying to make cookies, and there's a recipe that calls for butter, but you don't have butter, you have margarine, and you think that those two are basically equal, everywhere it says butter in the recipe, you just put in margarine. Similarly, if you have a system of equations and you know the value of x, everywhere it says x, you can just substitute that value of x. Let's see what that looks like in context. Someday, when you're traveling the world, you're probably going to have to exchange some currency. So you're going to have to deal with exchange rates. This problem says if 1 euro is worth $1.5 and $1.5 are worth 20 pesos, how many pesos is 1 euro worth? Well, we could write a system of equations. This symbol means euro. Now to solve it, you might notice that there's something that's the same on both of these equations. Namely, you might notice that that quantity, 1.5d, $1.50, shows up in both equations. Well, if you know that $1.50 is equivalent to 1 euro, then in the second equation, where it says $1.50, you can substitute 1 euro. So now you have 1 euro equals 20 pesos. Good to know. Here's a different conversion. If 1 yuan is worth $15 and $1 is worth 20 soles, how many soles is 1 yuan worth? Well, here we don't have something that's exactly the same on both, but we do know the value of d. And so we can substitute 20 soles, 20s in this equation, to where it says d in the first equation. That looks like this. You see how we just substituted for something that was equivalent to d? Now let's try it in a different context. You'll see a problem here. I'm going to ask you to go into Desmos, solve this problem, showing all the equations and all of your steps, and then come back here and we'll see how you did. All right, so here were the two equations that I wrote. Now that we have this system of equations, we don't have anything like x equals blank or y equals blank that we can substitute, but we can get there. And the way we're going to get there is we're going to take the second equation and solve it for x. We can do that by adding y to both sides of the equation. So we end up with x equals y plus 6. We can then substitute that in to where it says x in the first equation. So now we have y plus 6 plus y equals 156. We can simplify that to 2y plus 6 equals 156. Subtract 6 from both sides, divide both sides by 2, and we get the value of y. But we still haven't solved the question yet, because we don't know if 75 is the bigger or the smaller number. So here's the original equations. If we know the value of y, the value of x that makes each of these true should be the same. That's what it means for it to be a solution to the system. So let's try the second one. X minus, well, y is 75 equals 6. Solve that for x, we get x equals 81. I promise if you do it with the first equation, you'll get the same answer. So now let's answer the question. What is the smaller of the two numbers? The answer is 75. All right, there's just one more technique I want to show you before you go into practice, and that's elimination. Now, you've been using elimination all year to solve systems of equations. That's where you add two equations together and see that they're equal. But why does that even work? Well, here we have a black cylinder that's exactly equal to 5 pounds. You can see that the scale is balanced. Here we have a red cylinder that's exactly equal to 8 pounds. Now let's put the two cylinders on the left and the two blocks on the right. This is still balanced. Do you see why? Because we had 5 pounds and 8 pounds on the left, and now we have 5 pounds and 8 pounds on the right. If we add another black cylinder to the left and something equal to the black cylinder on the right, this will still be balanced, because we're just adding the same amount to both sides. That's the way that it works when we're adding equations together, because you have something on the left and something on the right. And when you're adding something else that's equal to the left and right, you're going to end up with something that is still equal. You're preserving equality. So now we're going to talk about solving equations using this principle. Suppose we have this same system of equations that we wrote before. We already know the solution. I just want to show you what it looks like here. Here's one equation. I've written it as it's on a balance. And here's the other equation. As you can probably guess, we're going to add these two equations together. And when we do, on the left we have x plus y plus x minus y. And on the right we have 156 plus 6. That simplifies to 2x equals 162. Now I want to make sure you know why we added them. We added them because we saw a plus y and a minus y, and we knew we were going to try to eliminate that variable. Because when we add those two together, the y in essence goes away. It's eliminated. We can then solve that fairly easily and get x equals 81. We can go on to solve for y, just like we did before. Here's a different equation that you could solve using elimination, except it's not as obvious, because if you add these together, you're not going to get any x's or y's to go away. You would get 4x minus 3y equals 30, and that doesn't help you so much. But what you could do is if you had 4y instead of y, then it would go away. So we can essentially add 4 copies of this equation to the left and right side of the balance. That looks like this. We had 4 x's and 4 y's to the left and 4 18s to the right. Let's see how much that actually ends up being. That's the same as 4x plus 4y on the left and 72 on the right. When we add these together now, we get 7x plus 4y minus 4y, that's going to go away, equals 84. We then divide both sides by 7, we get x equals 12. We could substitute that into either of the original equations to find the value of y. So the key to elimination in this case was figuring out that we had to multiply one of the equations by something in order to be able to eliminate the variables. Sometimes you can eliminate by multiplying both equations by something, just so long as you can end up with some coefficient and the negative version of that coefficient right on top of each other for the same variable. So elimination is a great technique to use when two equations have the same format, such as 3x plus 4y equals blank, 4x minus 3y equals blank. You have all the x's and y's on the same side. It's really easy to use then. Sometimes tricky to find what to multiply each equation by in order to eliminate one variable. So that's it. We've learned a few techniques for solving systems of equations. We can graph both and find the intersections. We can guess and check by finding the values that work for both equations. We can use substitution by replacing x with something equal to x, like butter and margarine. We can use elimination, adding and subtracting equations to eliminate a variable. With all of these techniques, it's going to be really important to check by substituting the values back into the original equation to make sure that it works. And with that, I'm going to send you off. Have a great time in Desmos. Bye.